Okay, in the last lecture we derived the partial differential equation for an individual undergoing a random walk, which is the first partial of the probability profile with respect to t is equal to the diffusion coefficient d times the second partial of the probability profile with respect to x. And we said that the probability profile initially was equal to the Dirac delta function, which basically stacks all of the probability onto the outcome that the individual starts at the origin. Okay, so with this PDE, we have to come up with a solution to generate the probability profile for the walker. And so to solve this, what we'll do is use what's called the Fourier Transform. Okay, so we apply the Fourier Transform, which says that the big F of P, which is going to end up being a function of C and then also time unperturbed, and is the integral from negative infinity to infinity of e to the I c x p of x comma t dx. So notice here the spatial variable is being integrated away, and we can think of this c variable as the frequency variable of the system. And so the first thing we need to do with this, we'll shrink things down here, move them up. The first thing that we need to do is to put down some properties of the Fourier transform so that it can help us out. Okay, so some properties. The Fourier transform, one of the best properties of it is that it's linear. Namely, we can factor out constants. So that's important. The other thing to notice is that if you take the Fourier transform of the partial of p with respect to t, it's going to be equal to the partial of the Fourier transform of p with respect to t. And we'll henceforth call the Fourier transform p hat. So it doesn't really do anything to partial derivatives with respect to time. Okay, so that's a few properties. We'll put those up in the corner for when we solve. And then most importantly, the Fourier transform of spatial derivatives are treated quite nicely as well. So if you take the first partial of p with respect to x, this is going to be equal to IC times the Fourier transform of p. And because this problem is second order in space, what we'll really want is the Fourier transform of the second derivative of p with respect to x. And all that does is tack on another copy of IC and then multiply by the Fourier transform of p. So notice this transform turns spatial differentiation into multiplication by I and c. So that's really nice. We've taken away, if we apply the Fourier transform to both sides, we've taken away one of the derivatives, and hence we'll end up with what's called an ordinary differential equation, which is substantially easier to solve. Okay, so let's transform our problem with those properties in tow. So let's transform our problem. Okay, so we have dp dt is equal to d squared p dx squared. If we Fourier both sides of this and pull out the constant d, we're going to have d p hat dt is equal to d, and then we're going to have IC squared p hat. And those are from the properties above. Now notice this is an ordinary differential equation for p hat. All right, to finish this problem, to a different screen here. All right, so far what we have is we have that the partial of p hat with respect to t is equal to d times I times c squared p hat, which I squared is -1, so this can really be written as negative d c squared p hat. This is again an ODE in p hat. We need an initial condition, and our initial condition from our PDE is that p of x 0 is equal to the delta function, the Dirac delta function, okay? And so what we'll just do is we'll transform both sides of that. So we'll transform our initial condition there. So we'll have the p hat, which will be at c comma 0, will be equal to the Fourier transform of the Dirac delta function with respect to x, which is the integral from -infinity to infinity of e to the I cx times the delta function with respect to x. And the properties of the delta function are simple. They just say take the integrand minus the delta function and just pick up the 0 term. And so that's just going to be equal to e to the I c times 0, which is just 1. And so our initial condition then, if we go up here, is just going to be that p of c0 is 1. Okay, so if we take those, all right, so again, dp dt is equal to negative d c squared p hat. That's a function whose time derivative is proportional to itself, and that's just a simple exponential function with the coefficient there being a coefficient for the t here, okay? And we know that p of 0 is 1, and so that is simply going to be the p of c0, because if we plug in t is equal to 0 there, it kills that exponential function. P of c0 is just 1, so we know that p hat, the solution of our equation in Fourier land, is e to the minus d c squared t. Okay, and then the last bit is to just transform back. So we have to take our p here and have it be the inverse Fourier transform of this function here, which if one goes to a Fourier table, one can see that it becomes e to the minus x squared over 4 dt times 1 over the square root of 4 pi t and then d. Okay, so this ends up being our solution to our PDE. And notice here, this is just a normal PDF, probability density function, with mean equaling 0 and variance equal to 2 dt, which makes some sense. If the random walk is unbiased, the expectation should be 0, and as time grows, or your diffusion is stronger, the variability away from 0 should also grow. Okay, well, I hope you enjoyed this video, and thank you for listening.